All right. Beep. Beep it a beep, beep, beep it a beep, 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 beep. Okay, so here we go, guys. We left off last time talking about colloids. And if you remember, solutions are homogeneous mixtures of multiple things being in one phase. A suspension is got particles that are so big they settle out. So this is a muddy river water. Pretty good example of a suspension. And if I fire my little concentrated heat beam through it, the laser gets blocked. Okay. The particles are huge, and eventually they'll settle out. I mean, this is what it looked like at the beginning of first period. Then you saw it settled out. And then you have colloids. If a suspension has a big particle size and it settles out, and a solution has a tiny particle size and dissolves, a colloid has a middle particle size. We did talk about colloids, right? Or did we not get that far?
No.
Oh, okay. So let's just go back a slide and talk about colloids. All right. So we talked about phase and saturation. We talked about soda pop and phase, and then suspensions have very big particles. Suspensions have very big particles, so big they don't dissolve. They settle out. So muddy river water is a great example of a suspension. Yeah, big particles that settle out. So Italian salad dressing is a suspension. If you leave it in your fridge for a long time, the big spices settle out to the bottom, and everything else is, get the idea. Yeah.
Not whole milk.
Yes, if it's not homogenized. So milk that comes out of the cow will actually settle out. Have you ever heard of the phrase, the cream rises to the top? Yeah. It basically means the really excellent will separate themselves from the losers. But it comes from the idea that as milk would cool down on your front porch in Minnesota, the cream would rise to the top, and you could basically see the phases of the milk. They would skim off that cream and make butter. But now an enzyme is added to milk, so it doesn't do that, because that would gross people out. So it's called homogenized milk. In fact, they used to put on the label, they used to write homogenized milk, and then that just confused people, so they stopped putting that on the label.
You don't like chunky milk?
Nah. If I want to eat cottage cheese, I'll eat cottage cheese. I don't want to eat chunky milk. But yeah, so they put an enzyme to keep the layers from separating.
Oh, like ogres.
So that's a suspension. A colloid has particles that are medium size. So a solution has tiny particles that dissolve. A suspension has big particles that settle out. A colloid has particles that are smaller than suspensions, but bigger than solutions. They're medium-sized particles that don't technically dissolve, but don't settle out. They get, I don't want to say suspended, but they get trapped in their medium. And because they are a special kind of mixture, we have special names for them. The colloids have two phases. The thing that would be the solute is dispersed, and the thing that would be the solvent is dispersing. Now there's 7 types of colloids. I'm not going to ask you to memorize what they are. If you're curious to learn more about colloids, you can always use your tube. But a great example of a colloid, smoke is a colloid. Smoke is a colloid of solid particles dispersed in a gas. Hair gel is a colloid. Hair gel is a colloid of liquid particles dispersed in liquids. Sometimes solid particles dispersed in liquids. Okay. Mayonnaise is another great example of a colloid. If you know what mayonnaise is made of 2 things. Actually, 3 things. Mayonnaise is oil, it's vegetable oil, egg whites, and salt. That's what mayonnaise is. Vegetable oil, egg whites, and salt. That's it. So the vegetable oil and the egg whites don't mix because egg whites are water soluble and vegetable oil is non-polar. So they whip it up, and the oil, which is non-polar, and the water compound, which is polar, they suspend each other. And the salt just chills out in the egg whites too. So, colloids. Yeah, gel's a colloid, smoke's a colloid. All right. Now, where I started, because I forgot that we didn't actually get this far in this class, where I started was talking about the Tyndall effect. The Tyndall effect is a way to separate solutions from colloids by using light. So here's my coherent light beam. My slightly out of focus coherent light beam. Do you know why Luke Skywalker's lightsaber was green in Return of the Jedi? You never thought about it, huh? Neither did I until I read about it online. So his lightsaber was blue because his dad's lightsaber was blue. And they made his lightsaber green in Return of the Jedi because the blue lightsaber light, the blue special effects, weren't showing up well in the desert. They're like, we can't see it. It looks really weird. The blue light in because there was the desert and a big blue sky. So every time he lifted up his lightsaber, the lightsaber disappeared in the special effects. So they had to use a different color because it couldn't be seen against the blue special effect background. Does that make sense?
Yeah, that's cool.
Yeah. So they had to they went in just with their computers and they just made it green.
Which kind of fit in with the new lightsaber.
And that just launched a whole new lore too.
Yeah.
They're like, once they did that, people were like, so a green lightsaber means a different kind of Jedi. Anyway, so in a suspension, the light just gets blocked. In a solution, the light, I got them out of order. In a solution, the light just goes right through. But in a colloid, you can actually see the light beam in the solution. Can you see the light beam in the solution?
Yeah.
If you're in the front, you just have to take my word for it. So you can't see it in a solution, but you can see it in a colloid. Okay, that's the Tyndall effect. It allows you to separate solutions, where the particles are itty-bitty and dissolved, to colloids, where the solutions are only itty and not dissolved. They're not itty-bitty, they're just colloid, colloid, solution, suspension. All right, so that's done. If you don't have a calculator, grab a calculator, because what we're going to be doing today is going to require a calculator.
Time to do some math.
Yep, time to do some math. And it's going to require proficient use of your exponent key. All right. So some of you are scribbling madly, trying to write down everything you see. I'm sorry you learned that. I'm sorry you learned poorly. That's not how you should do it. If I was summarizing this slide, I would say colloid, light seen in colloid. Solution, no light. Suspension, like blah.
Wait, solution, no light.
Solution, you can't see the light. So in a solution, the particles are dissolved and you can't see them. So the light goes in and comes right back out. In a colloid, the light goes in and comes out, but you can see it in the colloid. Hey, that's a colloid. I can see the light. That's a suspension. The light is blocked. All right. Disassociation. So we talked about what disassociation is. Disassociation is to separate, and with regard to ionic compounds, the ionic compounds disassociate into their ions. It's a fun word to know. Like when your parents say, that guy's a bad influence, you should disassociate from him. And you're like, no mom, I'm the bad influence. He should disassociate from me. So when a salt disassociates, it disassociates into its ions. Now sodium chloride is a simple example. There's one sodium and one chlorine stuck together, and when they disassociate, they make sodium and chlorine. So, question, how many moles of ions are in a solution of 1 mole of sodium chloride? Don't blurt it out, give me a number. Your options are 1 mole for every mole of sodium chloride, or 2 moles for every mole of sodium chloride. Do you think it is 1 or it is 2? Give me a finger, 1 or 2. For every mole of sodium chloride, how many moles of ions do you get? 2. You get 2. Yeah. For every mole of sodium chloride, you're going to get a mole of sodium ions and a mole of chlorine ions. So you're going to get 2 moles of ions. Does that idea make sense?
Yes.
One thing goes in, breaks into 2. Okay. So, any questions about that? Give me a thumbs up if you're ready to, if you understand this stuff. Okay. If you don't understand, put your hand away, wave it around. All right. So if you do understand, then what I'd like you to do is this. Identify how many moles, first of all, break these things into their ions, disassociate these 3 salts into their ions, and determine how many total moles are present when they disassociate. So we got copper sulfate. Remember, everything is binary. What does copper sulfate break into? How many total moles do you get? What does magnesium nitrate break down into? And how many total moles do you get? And what does sodium carbonate break down into? And how many total moles do you get? So do this on your computer. Everything is binary. So copper and sulfate. Everything is binary. No, we're not going to make
Sydney.
Don't fight. Don't fight. Don't, guys, settle down. Gentlemen, settle down. We're all friends here. We're all one big team. We'll leave the world better than we found it. Dude talks fast. I thought I talked fast.
Yeah.
That dude was a whirlwind.
Do the first one really quick, so like copper sulfate.
Yeah.
Because I don't want to like, I'm writing pen, I don't want to write like,
Okay.
get it right.
So the insecure among you want to do the first one together. So that copper sulfate breaks down into copper 2 plus and sulfate 2 minus. So for every 1 mole of copper sulfate, how many total moles of ions are we going to get? 2. We're going to get 2. 1 from the copper, 1 from the sulfate.
Oh, yes.
Precisely. Yes, this makes sense to me.
Oh, yes.
Oh yes, it makes sense. This is eminently logical. This is it. Gavin, you're done? So when you're done, go ahead and share your results with your neighbor and see who amongst you is the smartest.
Because
You're 6 times 10 things.
Dude, my goal in life is by the time I die to have like 1 mole.
and
Impossible.
1 mole of what?
1 mole of M&Ms.
1 mole.
Don't you remember how deep 1 mole of M&Ms would be after around the world?
Yeah, but like if it's over my entire lifetime. No?
Do the math.
Wait, how deep is it?
Do the math. Figure out how many days, let's say you live to be 100. How many days do you have left, assuming you have 84 more years? Divide by the number of moles to figure out how many M&Ms you would have to eat every day. Eat a mole of M&Ms.
I'm like 500.
I'm doing the math in my head, and it's more than exists on the planet right now.
Yeah, it's not looking that good.
Per day. We're talking about We're talking about billions and billions of M&Ms every day.
Imagine having to
Daily.
Work on breathing in oxygen molecules, a mole of oxygen molecules every couple seconds. Then you can say, I breathe in a mole of oxygen molecules every couple seconds.
More realistic.
Yeah. All right. Because a mole of oxygen molecules weighs or has a volume of what? Anyone remember what a volume of a mole of oxygen molecule is? 22.4 liters. Yes. 22.4 liters. Your lung volume is 2 or 3 liters. You can get that in a couple breaths. Okay. So, with a show of fingers, how many ions do you have in magnesium nitrate? Do you have 1, 2, 3, 4? I'm seeing a 3, a 3, a 3, a 4, a 2, a 3, a 3. I'm seeing lots of 3s, and that is right because you have 1 magnesium and 2 nitrates. You're going to have a total of 3 ions. And with sodium carbonate, you have 1, 2, 3. How many do you got? I see a 3, a 3, a 3, a 3, a 3, a 3, a 3. So lots of 3s, and that's right because you got 2 sodiums and 1 carbonate. Now, why is this relevant? If you have a compound that has more nitrates than magnesiums, then when you make your solution, you dump it in, the concentration of the nitrate is going to be higher than the concentration of the magnesium.
Yes.
Make sense?
Yes.
In fact, it's going to be exactly twice the concentration of magnesium. And if you put sodium carbonate in solution, the concentration of sodium is going to be exactly twice that of carbonate. Capiche? All right. Okay, give me a thumbs up if you're ready to move on. Put your hand up and wave it around if you want to talk about this more. All right. Okay, now we're doing the math. The math part of solutions is molarity. It's not hard. It's actually really easy. It's even easier than stoichiometry. I think you're going to like it. It's not hard at all. I brought to, when I give you solutions, I was like, this is 1 molar of this. This is 4 molar of this. This is 8 molar of this. Okay? Molar is just a shortened way of saying molarity. It's a way of expressing concentration quantitatively. So if I said this is concentrated, that would be qualitative. If I said this is 4 molar, that's quantitative. So it's a way of expressing a solution's concentration quantitatively. That means with the numbers. Yes, with numbers. Pound numbers. Pound. Hash pound. Hash pound. Hash browns. Hash browns with numbers. Okay. The formula for molarity, it's right there. It's going to be up there for a while. The formula for molarity couldn't be easier. It is just molarity, with a capital M, is mole per liter. Molarity is mole per liter. Couldn't be easier. It's how many moles you have in the volume of your solution. How many moles of your stuff in volume of your solution? Question? No. So that's molarity, mole per liter. Yeah. Yes. In fact, that's the next thing down here. You will frequently need to convert between grams and moles. So a typical exercise says, how many grams of this chemical do you need to make this molarity concentration? Okay. That's your typical exercise. And we're going to practice that on the next slide. Okay. So yeah, you will need to do a one-step T-chart to get from grams of whatever you need to weigh to moles, or from moles of whatever you need to use to the grams you need to weigh. That's what we're going to be doing on Thursday and Friday in the coolest lab ever. You get to bring home. You get to bring home a souvenir. No one in your No one else has ever seen it unless you have a kid that's already gone through this, or a brother or sister that's already gone through this. I'll just say 2 words. Golden pennies.
What?
Thursday and Friday. Don't miss it. Okay.
I know I don't.
Ready for some practice? Let's practice. Okay, we're going to start simple. What is the concentration in molarity when 3 moles of sodium chloride are dissolved in 2 liters of water? Yeah, some of you have already done it in your head. Okay. Molarity is just mole over liter. Yeah. If you put 3 on top and 2 down below, 1.5 molar. Okay, and that's how you'd read it. You'd read it as 1.5 molar. Now, pro tip, to reduce the amount of writing chemists have to do, if we want something in concentration, we put it in brackets. Okay. So if you ever see something in brackets, and you'll start seeing in the simulation we're doing on Monday, if you ever see something in brackets, that means concentration in molarity. Just to reduce the amount of writing, we put brackets. Okay, give me a thumbs up if you're ready to do level 2. Okay, you've mastered level 1, level 2. How much in liters of a 0.1 molar solution do you need to get 2 moles of solute? How much of a 0.1 molar solution do you need to get 2 moles of solute? So this is going to require you to rub a little algebra on the exercise. When you have an answer, show your neighbor. See if you and your neighbor agree. Remember, you can always check your work. Rub the number back in. We're going to do I'm going to ask you to volunteer with your hand.
You're trash. You missed by like 3 feet.
Yeah. She went up.
Do a question and answer. We're going to get the class, the whole class answer.
What?
Does anyone need more time?
I want to go pick that up for you.
Yeah, probably.
Once again, you're solving for a denominator here. So a couple techniques to solve for denominators. One is to divide both sides, multiply both sides. One is to put it over 1 and cross multiply, depending on what style your math teacher wants to use. Okay. If you got a number larger than 1, raise your hand. Oh no.
What?
You got a number larger than 1, raise your hand.
Really?
You should. Okay, so maybe we should do a little algebra.
Wait. You said you should get a number larger?
Uh-huh.
Oh, okay.
Yeah, you should. So do you want to try again?
Wait, what number should you get larger than?
Much larger than 1.
Yeah, okay.
Like 20 times larger than 1.
Like 20 times larger than 1.
Yeah.
Yeah,
I was
exactly.
about to say.
Yeah. So,
Shut up, Boca.
yeah, hopefully you got 20 liters. It's 20. Okay. So again, if you're having trouble solving for a denominator, you can multiply both sides by the variable you want, divide by both sides you don't want, or you can put this over 1 and cross multiply. You can just pick whichever math style you want to use. Okay, so I'm assuming if you're chatting you have questions about chemistry, you should be asking those of me, not your neighbor. Okay. Anyone have any questions? All right. Next. How many moles? Guys, and specifically ladies. Okay. How many moles of sodium hydroxide are present in 300 milliliters of a 0.1 molar solution? Now in this, you might want to rearrange this equation into another very valuable equation, and that is simply, when you rearrange it, you can say the number of moles I have is given by molarity times liters. Okay. Kind of nice. If you want to replace this by V, then you're more technical. You'd be like MV. So molarity, or moles, equals moles per liter times liters. So moles equals MV. Also a very handy equation. It's just this rearranged.
GC. Moles. Sorry, that's a weird color. Because it's
With
just
the red.
shiny.
Oh, yeah.
I see it now. Moles. Really.
I was going to put blinds in the back, but we demolished the building before we get to them. I didn't tell you that story?
No.
You should just paint them.
So, I'm not gonna do like the aluminum garbage, but so the old building had blinds. Wow, you guys were freshmen, right? Or were you even in
No,
school?
I was freshman.
Yeah, some of you weren't even in school yet. But the old building had blinds, you know, like the blinds you could move. And we wanted to put blinds in the new building, or right there in the back. And they said you can't install it.